One of the biggest puzzles in chemistry is trying to figure out what's actually in a solution when, well, all you see is clear liquid. It's kind of like trying to solve a mystery with absolutely no visible clues, right? But chemists have this totally brilliant technique for doing just that, and today we're going to break it all down.
So, picture this. You're in a lab. In front of you, a flask of hydrochloric acid. You know what it is, sure, but you have no idea how strong it is. Is it super weak? Is it dangerously strong? I mean, how could you possibly find out? Well, that's the exact problem we're going to solve today.
The answer to our little puzzle is this really elegant and honestly surprisingly straightforward procedure called titration. Think of it as the chemist's secret weapon. It's how they quantify the unknown and turn an invisible property, like concentration, into a real hard number.
So what is it exactly? Well, to put it simply, titration is this super clever method where you use something you know to figure out something you don't. You basically take a solution where you know the concentration perfectly, and you react it with your mystery solution until, boom, they've completely neutralized each other.
Okay, to make this happen, we've got two key players we need to know. First up, the analyte. That's our mystery liquid, the one in the flask that we don't know the concentration of. And then we have the titrant. Now, that's our tool, our standard. It's the solution where we know the concentration exactly. So you've got the mystery and you've got the key.
Now, doing a titration isn't just, splashing two liquids together. Oh no, it's more like a careful, precise dance of measurement and observation. Every single step is designed for maximum accuracy.
All right, so here are the core moves of this dance. First, you grab a super accurate tool called a pipette, and you measure out an exact amount of your mystery solution, your analyte, and pop it into a flask. Then, you add a few drops of an indicator. That's just a special dye that'll change color when the chemistry is just right. Next, you start adding your known solution, the titrant, from this long, skinny tube called a burette. And you add it slowly, drop by drop, especially near the end. And you've got to keep swirling the whole time. The second the indicator changes color and stays that new color, you stop. That, right there, is your endpoint.
And here's a little pro tip for you. Since you're literally looking for a single drop to make all the difference, it's a really good idea to do a quick, rough titration first, just to get a ballpark idea of where that endpoint is. Then, on your next few tries, you can go super slowly as you get close to that number. It's all about nailing that exact moment. Precision is absolutely everything here.
Okay, so the hands-on part is done. You've got your measurements, you've got your volumes. So, now what? Well, this is where we get to crack the code. We're going to take the numbers we just got and use some simple chemistry logic to figure out the concentration of our original mystery solution.
And it's actually a beautifully logical four-step process. The whole thing hinges on this concept called moles, which, don't worry, is really just how chemists count big groups of molecules. So step one, we use what we know, the concentration and volume, to calculate the exact moles of the titrant we used. Step two, we look at the balanced chemical equation to find the reaction ratio. It tells us how the analyte and titrant pair up. Step three, we use that ratio to figure out exactly how many moles of our analyte must have been in that flask to begin with. And finally, step four, we take that number, divide by the analyte's original volume, and boom, we get its concentration. See? It's just a logical chain of events.
All right, enough theory. Let's make this real with an example. Let's say we used 83 cubic centimeters of a 0.45 molar sodium hydroxide solution. That's our titrant, the known stuff, and it perfectly neutralized 235 cubic centimeters of a hydrochloric acid solution, which is our analyte. The mission, should you choose to accept it, is to find the concentration of that HCl.
Okay, first things first. We need to figure out the moles of our known substance, the NaOH. We're going to use that simple formula, moles equals concentration times volume, or N equals C times V. But, and this is a big but, there's a crucial detail here. The volume has to be in decimeters cubed, not centimeters cubed, so we've got to convert our 83 cubic centimeters by dividing by 1,000. Seriously, forgetting that step is such a classic mistake, so always watch your units.
So, let's crunch those numbers. We take our concentration, which is 0.45, and we multiply it by our converted volume, 0.083, and that gives us, let's see, exactly 0.03735 moles of NaOH. Awesome. Step one is officially done.
Okay, now for the really cool part. The balanced equation for this reaction, NaOH plus HCl, tells us that one molecule of NaOH reacts with exactly one molecule of HCl.
It's a perfect 1-to-1 ratio. And that is fantastic news for us, because it means that if we used 0.03735 moles of NaOH to get the job done, then there must have been, you guessed it, exactly 0.03735 moles of HCl in the flask. It's that simple.
We are so close. We're on the home stretch now. We know the number of moles of HCl, and we know the volume we started with in the flask. So all that's left to do is rearrange our trusty formula to solve for concentration. That's C equals N divided by V, or concentration equals moles divided by volume.
All right, let's do it. We take our 0.03735 moles of HCl, and we divide that by its initial volume, which, after converting, was 0.235 decimeters cubed. And there it is, 0.16 moles per decimeter cubed. And just like that, the mystery of the flask is solved. We now know the exact concentration of our acid. How cool is that?
Okay, that's all super cool in a chemistry lab. I get it. But you might be wondering, why does any of this actually matter? Well, let's zoom out from our little flask and see where this incredibly powerful technique shows up in the real world.
And trust me, the applications are literally everywhere. Titration is what's used to figure out how much vitamin C is in your juice. It's used to check the purity of medicines like aspirin. It's how they test the hardness of your drinking water, and even how scientists monitor the pollutants that cause acid rain. I mean, it is an absolutely fundamental tool for everything from quality control to environmental science.
So, when you really think about it, this isn't just some abstract chemistry exercise. From your orange juice to the air we breathe, titration is one of the key ways we measure and understand the world around us. It's a technique that truly makes the invisible visible.
And that kind of leaves us with a pretty fascinating thought, doesn't it? Titration gives us this incredibly precise window into the unseen world of chemicals all around us. It really makes you wonder, what other invisible properties of our world are just out there, waiting for someone to find the right technique to finally measure and understand them?